Okay, let's use NMR to work out a structure. So I'll give you an NMR spectra, and then you have to work out what the structure is from that. Okay, so we know that the molecular formula is C4H8O2. And this is what the spectra looks like. Okay, so we've got a triplet about 1. I've got a singlet at 2. And a quartet about 4. And we were given the integrated values of these. So the integrated value of this one was 3. This one is an integrated value of 3. And this one is an integrated value of 2. Okay, so how would we go about working out what that structure is? One of the most useful things you can get from the molecular formula is look at the ratio of carbons to hydrogens, right? Now this is CnH2n. It's not 2n plus 2. So that means that this molecule has got a double bond in it. They will never give you a whole spectrum of carbon-carbon compounds containing carbon-carbon double bonds because they're too complicated, but it has got a double bond in it. So it must have a carbonyl group. Okay, we know it's definitely got that in it. What else do we know? We also know that it can't be a carboxylic acid. Okay, and the reason why it can't be a carboxylic acid is because that gives you a ppm, a very high ppm. This hydrogen here would have a ppm of about 12, and we've got nothing anywhere near as high as that on our spectrum here, so it can't be a carboxylic acid. Another good thing to look at is, look, it can't be an alcohol either. The reason why there can't be an alcohol grouping is because this would have an integrated value of 1, wouldn't it? Okay, and we haven't got anything with an integrated value of 1 there. Let's look at those integrated values. Well, what have we got? We've got, this is an integrated value of 3. It's almost certainly going to be a CH3. This is going to be a CH3 as well. And this is probably a CH2. There's 2 hydrogens in that environment, integrated value 2, 3 hydrogens in that environment, and so on. And in addition to that, we know we've also got the we've also got a carbonyl, and if you look at the number of oxygens about, well, we've got another oxygen, haven't we? So I think that this is probably going to be an ester. So now the only thing we have to do is put all that together and see if it fits in with the spectrum. Okay, let's have a think about this CH3, right? This CH3, it's got a splitting of 2, hasn't it? It's a splitting of 3. It's a triplet. Let's just call that triplet. It's a triplet, so that means it's next door carbon with 2 hydrogens on. So that is probably next door to a CH2. So I think we can get these 2 little bits here, and we can say, right, we've got CH3, CH2. that CH3 is this triplet here, and these two hydrogens here is giving us this signal, and that's split into a quartet, isn't it? And it should be split into a quartet because it's next door to a carbon with 3 hydrogens on it. So we've definitely got that. Also, look at the chemical shift of this. The chemical shift of the CH2 is pretty high. It's 4. That means it is probably next door to an oxygen. We've got very little to worry about now because we've got our carbon now. Let's put that in there. And all we've got to think about is this CH3 up here, right? This one here with the integrated value of 3. So I put that there. And I think that is our structure. So I'm just going to rub some of that out a little bit, just to tidy up a little bit. Okay, so let's just write down there. So this bit we said before, yeah, this is this signal here. We're getting, that's a triplet. It's got a ppm of about 1 because it's a long way from any oxygens. This one is the quartet of a ppm of about 4 because it's next door to this oxygen. And these hydrogens here, well, that's going to give us a singlet, isn't it? That's going to be that there. Why is it going to be a singlet? Because the carbon next door to it has got no hydrogens attached. It's a carbon-al-carbon. Also, let's look at the ppm value of that. Well, that is the ppm of that is 2, which is very characteristic. Whenever you have hydrogens next door to a carbonyl, it has a ppm of 2. So that's our structure, and we would call that ethyl ethanoate. Before we finish the video, let's just have a look at the structure, what the spectra would be. It'd be very similar to that if we had a very similar ester. So let's pretend instead of that one there, let's just say we've got CH3, CH2. Okay, so it's a very similar. So once again, it's C4H8O2. This isn't ethyl ethanoate, this is methyl propanoate. Let's see what the spectra of that would expect to be like. Okay, so I draw. Okay, so this these hydrogens here, okay, that's going to be a singlet, isn't it? Because look, there's no carbon next door. It's going to have a ppm of about 4 because it's next door to this oxygen. So I'm going to put that one in there. Let's see, and it's going to be a singlet. It's a singlet, ppm of about 4. That's that there, and the integrated value, of course, will be 3. There's 3 hydrogens. Let's have a look at these hydrogens here now. Okay, that's going to be a quartet, isn't it? Because next door you've got the CH3 group. So that's going to give us a quartet. The ppm will be about 2. Okay, so that's going to be a quartet there. Why is the ppm 2? Because it's next door to a carbonyl. That's characteristic of it. And that will, of course, be an integrated value of 2. Goes to there. And finally, these hydrogens here. Right, there's 3 of them. They're next door to a carbon with 2 hydrogens, so it's going to be a triplet. And that triplet will be about ppm 1. because it's not near any oxygens. And of course, the integrated value of that will be 3. So quite a similar spectrum to the other one. The only difference is if you look, the quartet here is about 2. Quartet on this one is about 2 because it's next door to the carbonyl, whereas the quartet on this one is about 4 because it's next door to the oxygen. Okay.